Okay. All right, so it's just the first section. We'll just be going over all of the theory that we saw ever since the first tutorial session, but more precisely like the equations, because I mean this course is just based on all the equations. You could not understand any of the theory and still get an A+, just learning the equations by heart. And yeah, some of the exercises I got online, but like I didn't really have a lot of time to go over them, so I might not be able to solve them. But we'll see. We'll see at the end of the tutorial for that. So just right at the beginning, off the bat, we could have gone over a little bit about integration, but like I told you guys, the only integration you'll be doing is for that heat capacity equation, and it's really easy. It's just the integration of y to the power of n is just y to the power of n plus 1 divided by n minus 1, divided by n. So divided by n plus 1, sorry. So that's the only integration formula that you have to learn. On the other hand, interpolation, it's useful. Like this is generally how the theory presents it, and it's like it makes sense when you look at this equation, but learning this one by heart will allow you to be a lot quicker during exams, and is very essential for property tables. So don't miss out on it. Adam,
where is that integration formula?
I'll show it. We'll go over it soon.
Okay. Cool.
So that's mostly chapter 1. I pressure questions. So remember that it's very likely that you'll get a pressure question. I mean, you got one for the quiz, so it's likely that you'll get one for the midterm. Just to go over some vocabulary, because I do remember some of you asking me in the middle of a quiz what the hell absolute pressure meant. And please don't ask me that during a quiz. You guys should know that. Absolute pressure is the pressure relative to absolute vacuum, so compared to no pressure. So for example, most of the time that means that you have to take into account your atmospheric pressure, which in most cases will be this value. I would recommend that you learn it by heart. So just 101.3 kilopascal. That's you don't have to learn the other digits. Then you have gauge pressure, which is just absolute pressure, but you don't take into account atmospheric pressure. So if you were given, for example, the absolute pressure of a tank, which is at like 200 kilopascal, and they ask you for the gauge pressure, you just remove the atmospheric pressure. So 200 minus 101.3. And that just gives you like 99.7 or something like that. And yeah, and then vacuum pressure, which is just, well, should be, you're not really gonna need to use that ever normally. But it's just, by definition, it's just the pressure below atmospheric pressure. So just the atmospheric pressure minus the absolute pressure. Yep, yeah, that should be it for that. Generally, pressure, especially when you're studying objects submerged in fluids, will stay the same throughout its height. So it only changes with respect to height, and the lower you go, the higher the pressure, but it won't change horizontally. So like in this example, all these points have the exact same pressure. And if you move on, so just general stuff. If you want to calculate pressure for fluid 1 at height 1, you take, if it's absolute pressure, you take the atmospheric pressure, and then you add the pressure accumulated with the height of the fluid 1. So that's its density times the gravitational acceleration and times its height. If you want to go to fluid 2, you do the same. You add atmospheric pressure, the pressure you gain from fluid 1, and then the pressure you gain from fluid 2, and then so on and so forth. So that's only if you were to go down. So what happens if you go up? If you go up, for example, like if we had a container right on the side here, you would, and that we had like a fluid 4, for example, you would use this exact same equation. But since you're going up, you're relieving pressure. So you put minus density of the fourth fluid times G times whatever height you're climbing up to. So just the general rule, if you're going down, you're adding pressure, so you add the pressure value. If you're going up, you're relieving pressure, you remove pressure within the equation, which is basically the principle of manometers. Feel free to just unmute and stop me if you don't understand, by the way, because I'm just going to speed run all the theory or like the equations. Density. So as you know, like whenever a lot of the exercises we did in tutorial, we had to either change. We were either given mass, we were given mass and volume, and you either had to use density or a specific volume. And so density is given to you by mass divided by volume. You can find that out using the units as well. And specific volume is just right here. It's just 1 divided by density, or volume divided by mass. And it's just the reverse of density. Specific gravity, you could have an exercise that just asks you, gives you a fluid in terms of specific gravity. And that's just, if they give you the specific gravity, you just have to multiply it by the density of water, which in SI units is 1,000 kilograms per meter cubed. So just multiply it by 10 to the power 3, and you should get the density of the fluid, which then can help you, I don't know, get you the specific volume, or you need to use the density, depends on the exercise. I recommend that you learn these values. It's always not just useful for this course, but useful for many courses. So density of water in SI units is 1,000. In imperial units is 62.4 pounds per feet cubed. Constant of gravitational acceleration, we are not in civil engineering, so we're not going to put 10 here. It's 9.81. And in imperial, it's 32.2 feet per second squared. Last thing is specific weight. I haven't seen it in a lot of the exercises, but you'll go over it a lot. For example, you'll go over it a lot in the Bernoulli equation, which is more like fluid mechanics, so fluids 1 and fluids 2. So specific weight is just the density of the fluid that you're studying times the gravitational acceleration. That's all it is. Okay, so make sure you memorize these equations. Okay, so yeah, like I explained before, but here are more details. Actually, let's see if this works. Yep. So let's say you have this pipe system that just zigzags all over the place, like that. All right, just imagine it's a pipe. And you have different kinds of fluids inside. Oop, 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 like that. And it goes out. Actually, let's make it go back up. And then if you remember, if you put these kinds of symbol, so if on a fluid you see, like, let's say it's in a beaker right here, you see this symbol or this symbol, usually means that it's touching the atmosphere, hence you assume that it's atmospheric pressure. So let's say we have to find the pressure at, I don't know, here in the middle, knowing that on both sides it's at atmospheric pressure. So usually we select a point to start in which you know the pressure. So for example, here, let's say actually it's contained and there's only like a pressure inside. So you can assume that it's given in the exercise as P1, or you can start here because you know it's atmospheric pressure, and you should know that atmospheric pressure is 101 kilopascal. So that you select the point to begin, and then you follow a path all the way to the point that you want to know the pressure of. So let's say this is the point I want to know the pressure of. We go down all the way here, we go up all the way here, we go down again, and then up again. So like I explained before, if we're going down, like in this first section, you add the pressure with the properties of said fluid. So the density of the fluid times G times the height that you're going down to. And if you're going up, like I said before, you remove that set pressure with the properties of the fluid. If you're going horizontal, obviously don't change anything. You're not, unless you're not, even if you're changing fluids, it doesn't really matter. So let's say like here is changing fluids, the pressure remains the same. If you're going down though, then you're gonna have to use the properties of the other fluid that you've crossed. So yeah, and then at the end you should get an equation that leads to that you make it equal to the pressure that's here. So let's say it's equal to like P2. Here, let's replace, so to make it applicable, replace P1 by P2. And then you just calculate, hopefully that the exercise give you all the equations that you need, or the values, and you can get P2 simply just by doing that. If instead you were given, well, like we saw, specific weight, remember to use this equation instead, which is a lot simpler. And yeah, wait, that's not the right equation. I forgot to correct that. That should be H, not G. So yeah, the height times the specific weight will give you pressure, because specific weight is just density times G, just like we saw before. Yep. Okay. On quality, that was also a question that was asked of me during the quiz. Again, don't do that. Learn about it before. Quality is the mass fraction of the saturated vapor within the total mass of your mixture. So you're most likely going to be in a mixture phase, and it's either going to be near zero. If it's near zero, that means it's mostly in the liquid phase. If it's near 1, that means it's mostly in the vapor phase. If it's equal to 1, then it's only vapor. If it's equal to 0, then it's only liquid. If you are in the compressed liquid or in the superheated vapor, I saw that normally if I was the one to grade and you put, I don't know, 0 for the compressed liquid or 1 for the superheated vapor, I wouldn't have removed any marks for you. Whoever's grading is pretty strict. So if you know that you're in the compressed liquid phase or the superheated vapor phase, just put 2 marks or like an X or just something to indicate that it's not between 0 and 1 or equal to 0 and 1. And this is how you calculate it. Normally, it's just the mass of the saturated vapor divided by the total mass. So the total mass will just be the mass of the saturated vapor plus the mass of the saturated liquid. And you can apply it to this equation where, well, here they show it in the specific volume, but you can replace specific volume by any specific property, really. So you can, I don't know, specific enthalpy, specific entropy, et cetera, et cetera. Okay. I guess we'll go over subscripts later. This is another way of getting quality, although I don't think you'll need this anyways. If they give you a graph within the exercise and they give you a point where the mixture is, so let's say it's at point B, what you can do is just apply this equation. And again, you can replace it by any specific property. So in this case, Y can be replaced if we were to use this graph by specific volume. So the specific volume of the mixture minus the specific volume of the mixture if the mixture was equal to, had a quality of 0, divided, sorry, by the specific volume of the saturated vapor on the line minus the specific volume of the saturated liquid on the line here at A. So VC minus VA, pretty much. PV or TV diagram. So I talked a little bit about the different phases that you can get. So you have a total of 5. Technically, they should try and memorize. There were some exercises in the problem pack. If you remember those tables that could ask you what phase you are in, and which also appeared in the quiz, by the way. So you can get compressed liquid, you can get saturated liquid, the mixture phase or mixture region, saturated vapor, or superheated vapor region. And yeah.
So how do you exactly know what phase you're in based off of, for instance, like temperature or pressure values that would be in a table?
Usually using the property tables method. You can't know it off the bat. Obviously, you have to use the tables. So let's say, I don't know, let's say you have a pressure of 650 kilopascal. Usually if an exercise gives you pressure and temperature, unless it's directly indicated, like say, actually, it's just pull out the property tables. Sorry, just give me a second. There we go. Okay. So we go down to the tables that we need. So let's say we're using water. We're given in the exercise pressure of, let's say, I don't know, 300 kilopascal. So you go down to 300 kilopascal or 0.3 megapascal. And they also give you a temperature of 133.55. Then you would know that you are directly in the mixture phase because it's directly correlated to this. Now, if you have a pressure of 0.3 megapascal and you have like a temperature of 150 Celsius and it's not equal to this temperature that's here, then you directly know that you are not in the mixture phase. You would either be in the compressed phase, the compressed liquid phase, or this superheated vapor phase. Did that yeah.
Okay, right. So based off of that temperature and pressure that you're given, you could kind of figure out amongst which table that you would have to be looking in.
Exactly.
Okay.
Usually I would always look first into the saturated mixture phase because that makes exercises more complicated and profs like that. So you
what
would,
page is that again?
Sorry?
In the PDF, what page is that?
It's page 7. Now it goes for a while. I mean, it's just page 7 and after that. I mean, there's in between that, it'll be for water, and then you get some tables like the compressibility factor graph that you have, and then after that you'll have the ones for the refrigerant. But again, you start with the mixture phase, you see that the temperature or pressure that's given to you does not fit, then you check. Either you can start by the superheated tables, and if it doesn't, you don't see anywhere that you have 0.10 megapascal and I don't know, a temperature that's not in between these values, and it's likely that you're.
What pages though exactly then would I have to run through? You said to start on page 7, right? That's like the best one to go for first.
Well, they're not going to give you the whole pack. If during the exam, just like they did with the quiz, they'll just give you a page with I think they gave you like the tables for the mixture phase, the superheated phase, and the compressed liquid phase, but they didn't give you all of them. And it was just for water, so you won't have to like sift through, luckily for that.
Okay, so what we got on the quiz was basically, because I have it right here, the paper with me, so that would be the ideal tables to look at to figure out these types. Okay.
Yep. So just to recap, if you're within these tables, thanks to the properties that are given to you during the in the exercise, this means you are either in the mixture phase, in the saturated vapor phase or the saturated liquid phase. We'll go over that. If it's not in these tables, you go over to the superheated vapor tables. If it's not in the superheated vapor tables, then it's in the compressed liquid tables. If it's not in that, then either you made an error or, well, I don't know, you discovered a new liquid. Now, since if you were in the mixture table phase, then that means you can have three different types of fluids, three different types of phases. You can either have mixture, complete mixture phase, saturated vapor, saturated liquid. How do you know which ones you are in? Usually each exercise will give you another property, or that you have to find yourself. I don't know, for example, they give you mass and volume. With that, you can find specific volume. And let's say in the exercise, we are given water. It's at 55 Celsius. It's at a pressure of 15.758 kilopascal. And we are at a specific volume of, let's say, I guess, 7. So our specific volume of 7 meters cubed per kilogram. It's not equal to the saturated liquid specific volume at this specific temperature and pressure. It's not equal to this specific volume of the saturated vapor at this specific temperature and pressure. Therefore, you are in the mixture phase. You are in between these two values. If you are not in between these values and you're directly equal to these values, then that means you are either, so if it's equal to 0.001, you are in the saturated liquid phase. If it's equal to 9.568, you are in the saturated vapor phase. So if it's in between, you're in the mixture phase. If it's equal to the saturated liquid, you're in saturated liquid. If it's equal to saturated vapor, you're in saturated vapor.
Sorry, I just had a question.
Mm-hmm.
What if it's not in the interval?
If it's not in the interval, that means it's not in the mixture. That means it's in the other tables. Okay, perfect. Thanks. If somehow you are given that temperature, like again, 55 Celsius and 15.758 kilopascal, and it's not in between, then something's wrong. Something's off. It has to be in between or equal. But don't we normally only have two properties, like for example, temperature and specific volume? Yep. Yeah, normally. Yep. Okay. Thank you. And so, yeah, actually, good question. If you're only given like temperature 55 Celsius, but then they give you a specific volume of 7, then you see that it's in between these two, then you know you're in the mixture phase. If you see that it's not in between or not equal, then you need to look into the other tables. And for example, sorry, for example, if it's like, for example, 10, the specific volume, for example, if it's 10, do we look in these superheated? Or I mean, that's just if you have general knowledge. Let's see here. It's roughly close to here. I mean, usually what they'll give you is somewhere obvious. I mean, if you were to study these tables, I guess, yeah, here is superheated water. You see that as the temperature rises, the specific volume rises. And as the pressure rises, actually the specific volume decreases. In this case. Okay, thank you. And super compressed liquid, temperature rises, and yeah, no, it's kind of hard to tell. But usually, just like with quiz 1, they don't give you the whole packet, so you don't have to take that much time to sift through. Okay. Here, yeah, we're here. All right, so there's different ways that you can use these diagrams. So kind of just like the way that you use your tables, you're given like a pressure that's around here, and you're given a specific volume. Let's say that's around here. Then all you have to do is draw a line here and here. Now you land here. What does that tell you? Absolutely nothing. besides that you're in the mixture phase. You can't pull out any other property with that. If, on the other hand, let's say you were here, let's say it hits the line exactly right here, then you could go into your tables. You know that you were in the saturated liquid phase. You could pull out the temperature. Actually, no, in both cases, you could pull out the temperature. But let's say actually in another case, you're given pressure and temperature. So actually just like those lines that you see at the top. So, and it's given to you that you're in the saturated liquid phase. You could find the specific volume. Now, if you're right in the middle, then you can't really use it to find any other properties. In this case, because pressure and temperature are dependent from one another. If they're not, then you can use the tables to find it, or ideally they give you a graph and they give you the line directly, and you just have to plug in the values and the pressure, and you can find it. So sorry, I'm explaining this badly. Like for example, let's take, let's say this is P1, and the corresponding line that I just drew is for T3. And you're giving this line, and they tell you to find the specific volume. You have the specific volume for this entire line. Wait. Yeah. So you just draw across with pressure 1. Once it hits the line and you go down, you have your specific volume for this state. Let's say your pressure, you were given a pressure at, let's call it P3. That's right over here. And it's still the same temperature. You go across. You go across right when it hits the line, put an X, go straight down, vertically down, right where it hits specific volume, and that'll be your specific volume for that value. And now the issue here comes when actually, if you were at P1 and you would go straight across, you wouldn't know which specific volume would be. So you can't really use this graph if you're in the mixture phase. It's only if you're in the compressed liquid phase or the superheated phase, but usually they don't really give you this kind of exercise. So yeah, just like here, if you have a compressed liquid, superheated vapor, saturated liquid, or saturated vapor, even saturated liquid or saturated vapor shouldn't be included here. It's only compressed liquid and superheated vapor. You can use the temperature, or well, in this graph, the temperature. In this example, is 374.14 Celsius. You're given a pressure of 22.09 megapascal, so you have to use this specific line. You go across with the temperature. Once right when it hits the line, which in this case is the critical point, you go down and you can find the specific volume. Now, let's say we, I don't know, we're at 350 and our pressure is at 15 megapascal. 350. And it hits the line like right over here, right where it's horizontal like that. Then it could be, the specific volume could be in this entire region. So you can't find the specific volume in this case. Only when it hits the line here or I don't know, here in this case. But in these regions, you can't find it. So usually the exercise will give you another method to find it. Okay. Triple point, I mean, that's just the cool state where a fluid is in all states, but again, that's not really useful to find exercises. And I think one of you told me that theory won't really be covered in this exam, so I wouldn't really too much about that. But just to recap, it's when a fluid exists in all sorry, a substance exists in all three states. Okay. So I did record this tutorial when we went over this that explained this really well, but I'll try and do it again. So just kind of like what we saw, we in your Moodle, you have property tables. It goes over a bunch of the different properties that you have for different substances. Won't go over too much in detail, but mostly like the most important ones, just like I told Adam, will be from page 7 to all the way at the end. So it's just all the properties that you'll get for the mixture phase, the superheated phase, and the compressed liquid phase for both water and the refrigerant. Yeah, recap, these pages are very important. And yeah, remember the state postulate that you need 2 independent properties to find whatever other properties. So for example, if you have a specific volume and temperature, these 2 properties are independent from one another, and you can find all of the other properties. But as we saw, if you have temperature and pressure and you're in the mixture phase, these 2 are dependent, so be careful, you can't use them. So yeah, exercises will usually give you 2 of the following properties: mass, volume, specific mass, etc., etc. It is possible that you'll be asked to deduce an intensive property out of 2 extensive properties. The most classic example is when they give you mass and volume, and you can just either find density or specific volume with that. And once you have 2 intensive properties, you can just find everything with the table, the property table, or using quality, or well, I guess the 2 equations that you could have to use when using property tables is quality and linear interpolation. Yeah, again, please practice using these tables. Like I said, it takes longer to sift through them because there's more tables, but once you get the hang of it, it'll be a lot easier when you just have 1 page to sift through during the exam instead of like 16 or 15. Just a quick reminder, sometimes you can see this subscript for like a specific property. It just means that for this set property, it will be the intensive property of the saturated gas minus the same intensive property, but instead for the saturated liquid. Yeah, again, this is just a recap for quality. You can just replace Y by any of the intensive properties that you're studying. And oh yeah, general rule, this is pretty important. Hopefully you won't have to encounter that during the exam, but it's better to just know it, and it won't be a worry for you. So at pressures that are below 5 megapascals for the saturated liquid data and compressed liquid data, just use the properties at the same temperature. So actually, let's just show that property tables. So yeah, right here. So this is as deep as it goes, as low as it goes for pressure. You won't go any lower. So if for example, you know that you're in the compressed liquid water state, but your pressure is at 2 megapascal, just use this table. Just use the table. You're given, I don't know, 80 degrees Celsius, then you just use this line. Even though it's not equal to the same pressure, that's just the general rule. Ideal gas equations, so I believe that's chapter 3. So the theory behind an ideal gas is that it's at such a low pressure that it's directly proportional to the temperature T, so Char's law, and inversely proportional to the specific volume. And so you can get these equations. You can either, again, like I said during tutorials, learn them by heart or know how to get one from the other. So learn the first one, but you know that specific volume is mass divided by volume. So you can get this equation or just replace it by density. because specific volume is the inverse of density, et cetera, et cetera. Just remember that R and RU are different values. So R is the gas constant for the gas that you are studying, and RU is the universal gas constant of 8.3145 joules per mole times Kelvin. And always, general reminder, please change your temperature from Celsius to Kelvin. You're multiplying it, so in this case, it's very important that you keep it in Kelvin instead of Celsius. Yep. Moving on. This or that later. So if you have an exercise that states this is not an ideal gas, you have to use compressibility factor. So this is the equation for compressibility factor. It's also should be given to you in your property tables. In the method to find it normally, it doesn't go over this slide. So if Z is equal to 1, you know that you have an ideal gas. If you stray further away from 1, so you're at, I don't know, -5, or if you're at 15, then you're going further and further away from being an ideal gas. And the more likely it is useful that you use this equation. So in order to get it, the first step is to obtain the critical point properties of whatever substance you're studying. So in this case, let's take the refrigerant, which is right here in your property tables. I think it's in the first page. You take the critical point temperature, which is 374.3 Kelvin, and then your critical point pressure, which is 4.067 megapascal. And then you, once you have that, you divide the pressure that you got from the exercise by the critical point pressure, and then you divide the temperature that you got from the exercise, or that you calculated, by the critical point temperature. Then you get what we call PR and TR, or reduced pressure and reduced temperature. Once you have those, you use this graph. So go down here, you plug in whatever reduced pressure you found. Let's say it's, let's take, I don't know, 1.5 right here. Whoop. And let's take a TR value, which you see goes from 1, 1.05, 1.1, 1.15, 1.20, etc. Let's say it's at 1.20. You found that it's at the TR is 1.20. You go all the way up. You hit TR line right here. You go horizontal, and you get your Z value of 0.7. You plug that in into this equation, and I don't know, like, I guess the exercise asks you, hey, what's the specific volume, or what's the gas constant, and you can find it using this this equation. I don't know what exact graph they'll be using it, but this one's really useful. Not only does it give you the equation, but it also gives you the reduced pressure and reduced temperature equations, which is really nice. And also the pseudo reduced volume equation, which I haven't seen too much, but we actually did have an exercise in one of the tutorials where we had to use this equation. So I would memorize it. Yeah, just going over it now. So if you have to use the VR line, you calculated the VR state, or you can't use the temperature for some reason, I don't know, it's not given to you, or the pressure is not given to you. Or actually, no, pressure should always be given to you. For example, temperature is not given to you. You would use the values that are going diagonally this way. So for example, let's take PR again at 1.5, but your VR is at 1. So you would go up, 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 up to this line here of 1, and just do the exact same thing. Go straight here, and it's, I think, I don't know, 0.88 or something like that. There's a great exercise we saw last tutorial. It's in the slides that we could, maybe if you guys want, we could cover again today. That goes over a pseudo reduced volume. Yeah, and also, yeah, exercise 3.7 is a great exercise to get comfortable with all three methods. So all three methods here is the property tables method, the ideal gas equations method, and the compressibility factor method. Okay, any questions? I see some, I don't know if I skipped some hands. Okay, keep on going. So specific heat, just like I said before, that's the only one that you'll have to integrate. And I mean, this is the equation that you'll have to integrate. Like I said before, it's really easy. It's just t to the power of something. And so just let's assume t to the power of n. Integrate that with respect to t. It's just going to be t to the power of n plus 1 divided by n plus 1. That's it. That's the only integral that you have to know. Yeah, and in order to, well, just to go over a little bit of theory, just like I think we went over this last week, specific heat is just the energy. So remember, energy is usually in units of joule. The energy required to raise the temperature of a unit mass substance by 1 degree, with either the volume being constant, so in this case CV, or the pressure being constant, so CP. And you can find CV, CP, or the change in specific enthalpy or specific, oh no, so this is specific internal energy or specific enthalpy using these equations. And yeah, you would integrate it with respect to the two different temperatures that you find for the two states that you're studying, and get the value. Now, just a reminder. For example, if you're studying oxygen, you use this equation and you plug in the constants, so A, B, C, D, with these values right here that align with oxygen. Now, the CP value that you'll get, so be careful about this, is if you were to use this equation, is in kilojoule divided by kilomole times Kelvin. Now, we usually don't use kilomole. We like to use kilograms instead. You'll usually be given a constant that allows you to switch from kilojoule divided by kilomoles times Kelvin to kilojoule divided by kilograms times Kelvin, which is also something we saw last week. Yeah.
Hey, just a quick question. If we get a constant like that, is it like applicable within that certain problem for that given material? So it's like pre-calculated in a way?
I don't understand the question. Sorry.
You're trying to say that like you would be given a constant that's like applicable to the molar mass of that substance that we're using for that given problem? Is that why we get a constant?
Yeah. Unless they're trying to trick you where they give you the constant, but they give you like an equation that directly gives you kilojoule divided by kilograms times Kelvin. Yeah, no, obviously it'll be applicable. I don't think they'll do that. I just remember like when we went over this specific exercise that goes through this last week, that they gave you the constant directly in their exercise. Actually, no, they didn't give it to you, and they didn't, there's nowhere in the property tables pack that is given to you for you to find it. So yeah, definitely they'll give it to you. No way you would have to know these constants for all of these substances. No way. So don't worry too much about that.
Okay.
Enthalpy, again, went over that last week. So the sum of the system's internal energy and the product of its pressure and volume, but that's the literal definition. So if you just look at this equation, it's the same thing as the literal definition, but the theoretical definition is just how much heat content energy is within something, or like a control volume. But I don't really, it's hard to like wrap your head around that. So just remember the equation instead. And yeah, just notice that this one is of specific properties, but you can switch around, just multiply everything by mass and you're good. Okay, go over first law of thermodynamics is really sure that you're gonna have to, well, if not that law, if not these equations, definitely, you will definitely have to like have these exercises for sure using these equations, but we'll go over them one by one. So first law of thermodynamics is just the change in energy is equal to the produced heat in a controllable volume and minus the work that is created. So work, the reminder, is just in a vector format, F times the distance that you're covering. So, but most of the time we'll just do one dimensional. So you can ignore the vector format and just go straight to this equation. So force times distance, whatever distance was covered. Yeah. So energy E usually can be decomposed in 3 different types of energies. Like I said before, it can be a lot more. We have a lot more types of energies in the world, but these 3 are the only ones that you're going to be studying in this course. So internal energy, energy that is created by the interaction of atoms and molecules. Kinetic energy is just how fast you are going, and potential energy is usually just how high the substance is relative to a gravitational field. Again, reminder that energy units are in joules, so this whole equation is in joule, and joule is newtons times meters. So that actually just goes back to the equation that we just looked at. So force times distance is newtons times meters. And when you sum all of these up, you get E. And the equation to find kinetic energy is 0.5 times mass times the velocity you're going at squared. Then the potential energy is just the mass of the substance or whatever you're studying times G and times the height. And with the first law of thermodynamics, if you were to decompose delta E a little more, you can just recognize that this is a specific internal energy. This is the kinetic energy, and this is the potential energy. And yeah, you see this equation has dots over them. That means their rates. So they're properties that we're studying over a course of time. Yeah, I haven't seen too many exercises where you had to use that, thankfully, because they do tend to get long. But I would definitely try, or hopefully it's, I don't know. Did the prof tell you if you were getting an equation sheet?
Not that I know of.
No. She definitely like send emails or whenever her office hours are and ask her, hey, are we getting an equation sheet? Because this one's quite long. Worst case scenario, memorize it, but yeah. You can change the equation in this format, but it's just the exact same thing as this. Okay, so these are a lot more important, and again, like I said, will definitely show up next week. When you're applying the first law of thermodynamics, or an exercise asks you, hey, how much work am I creating in this piston cylinder or whatever system I have? Knowing that I am in a isobaric state, so the pressure, it remains constant. That's what isobaric means. You would use work is equal to the pressure times the change in volume. So the volume in the final state minus the volume in the initial state. You can change obviously this equation with a specific volume. If you multiply, make sure you divide everything by mass, and then multiply it back again. And yeah, that's the simplest of all the work equations that you'll have to use is the isobaric one. And I forgot to correct this one. This is the second one that you may have to use is the isothermal one. So if the temperature remains the same throughout the change between two states, so work is equal to this equation, and you can replace nRT with pressure times volume if you have an ideal gas or other like forms of I believe it was The most common one was mass times gas constant times temperature, if I'm not wrong. And then that's multiplied by the, well, this can be rewritten another way. Logarithm of the volume, the final state, divided by the volume in the initial state. This parentheses can be rewritten in this way. Okay, so these are the first two methods of how to get work if you have an isobaric or an isothermal state. The other one is a polytropic process. I'm sure you've encountered in some of the exercises. The polytropic process just means that the process is reversible, so you can go from one state to the other and then back. But we don't really care about that. We care about the equations. In this case, we have a couple of equations that will concern you. We have this first one, so pressure times volumes to the power of n is equal to c, where both n and c are constants. N will usually be given to you, and it's, well, most of the time like 1.3 or 1.4. But again, it will always be given to you. And c is always, most of the time, given as, since we're in a reversible process, the pressure times the volume to the power of n in the first state equal to the pressure times the volume to the power of n in the second state. And this is the first work equation, first form of the work equation. Now, if you're in an ideal gas, the polytropic equation can be rewritten this way. Makes it simpler if you, I don't know, you don't know the volume between those two states, you just know the temperature, you can just use this equation. And thanks to that, you can also rewrite the p to the power p times v to the power of n in these forms, which again I would recommend that you learn by heart. I know it's a lot to memorize, but a good way to memorize is just to do so many exercises that it's stuck in your brain. That's how I did it, and you just memorize these equations by heart using that method. This other form of the p times v to the power of n, you don't need it to be in the ideal gas state. It's just reshaping this equation. And if you were to have n equals to 1, which every math teacher should have told you by now that you can't use these equations because then the denominator would be equal to 0, you use this equation instead. Which is, well, actually it's just this equation actually. Just being an isothermal equation. The last method that they could ask you to find work is using the first law equation. So I don't know, you may have to calculate the mass flow rate. I don't know, they give you mass and they give you time, so you just divide mass by time. They give you pressure and temperature, and with that, with the property tables, you can find specific enthalpy. They give you the velocity, they give you the height. They tell you, oh hey, this process is entirely adiabatic, so this means that Q is equal to 0, so no heat is produced. You just plug in all the variables that either you found or they just give you directly, put work on one side and everything else that you know on the other side, and just solve for W. Okay, did we go over everything? Yeah, I think so. Okay, any questions going for the theory? Anything that I missed that you would want me to cover? Okay. So this is the first exercise of midterm, the first midterm in 2017. I forgot which semester, but that doesn't really matter. I haven't gone over it, like I said, I didn't have a lot of time to prepare. So let's just cover it now. Energy is added to a piston cylinder arrangement, and the piston is withdrawn in such a way that the temperature, the quantity, pressure times volume remains constant. So we're in an isothermal process. The initial pressure and volume are 200 kilopascal, 2 meters cubed, respectively. And the final pressure is 100 kilopascal. Calculate the work done by the idle gas on the piston. Okay. Actually, can I? So just like we did before. State 1. P1 here given as 200 kilopascal. V1, 2 meters cubed. T1, let's just say T1, T2. State 2. T2 is 100 kilopascal. V2, we don't know. T2 is equal to T1, aka isothermal. Okay, and they tell us ideal gas. So just to recap, isothermal is P1 in the first state, V1, ln, V2, V1. Now in this case, we don't know V2, but we're given the hint that we are in an ideal gas. And so this actually goes back to, well, actually, this equation that you can use if you're in an ideal gas equation in between two processes. You can just use this equation. It can actually be really useful, and in this case, will actually get us the second volume that we need. So V2, that's a P2, T2, P1, V1, T1. We know that T1 is equal to T2, so we can just cross those out. Single out with respect to V2, so that gives us P1, V1 over P2. So 200 times 2 divided by 100 is equal to 4 meters cubed. And then you plug that into your work equation. So 200 times 2 times ln of 4 divided by 2, which is just going to give you 2. And that gives you 277 kilojoule. Okay. Any questions regarding that one? This is one thing I forgot to describe actually, is that you see here that we use the pressure and the volume in the first state here. If you're questioning which one you should use, it's always in the initial state in those first two, or whatever subscript this one is using. So if we were to go back to, I don't know, this format, so Pn, Vn, Ln of F, let's say, minus Ln parentheses of Vn. These subscripts or state, whatever state they're referring to, are always the same. Okay. All right, next one. A cylinder device fitted with a piston that contains initially argon gas at 100 kilopascal and 27 Celsius, occupying a volume of 0.4 meters cubed. The argon gas is first compressed while the temperature is held constant. So just like last time, isothermal, the volume changes to 0.2 meters cubed. So this time we're given the pressure, the volume that changes, but not the pressure. Then the argon is allowed to expand while the pressure is held constant. So isobaric process, and we're given the volume change here. Determine the total amount of net heat transferred in the argon in kilojoule. Okay, so just notice here that they're asking for the net heat transfer and not the work. Okay. So same method as before. What I like to do, state one. P1 is equal to 100 kilopascal. T1 equal to 27 Celsius, which if you convert to Kelvin is just 300. And a volume of 0.4 meters cubed. State 2. P2 we don't know. T1 equal to T2. P2 equal to 0.2 meters cubed. So just like with the other one, take work equal to P1 V1 ln of V2 V1, but in this case it's well, it's P2 that we don't know, but in this case we don't really care because we don't use P2. So we just have to plug in everything. 100 times 0.4 ln of 0.2 divided by 0.4, which is going to give you 0.5. And that gives you a work of 27.76 kilojoule. Okay, so this is for the first state. One to two. Now we take the third state. P3, well, we don't know, besides that it's equal to P2. T3, we don't know, but that will not be useful. And we know that V3 is equal to 0.6 meters cubed. Now for an isobaric process, just like I told you, it should be, let's see, 3 will be equal to pressure that is being used, which we don't know, and the change in volume. So in this case, V3 minus V2, final volume minus initial volume. So in this case, we have to find pressure. In this case scenario, we just have to, oh yeah, there it is. There's the hint. It's an ideal gas. So we just do like the previous exercise, but we just don't take temperature into account. In this case, if we were to do this between state 2 and state 3, we'd have two unknowns, so both temperature and pressure. So we wouldn't be able to use, what was it, PVT equal to PVT. So two unknowns for one equation, you can't solve that. But if you remember, with state 1, we are given temperature and we are given pressure. So, and we are given volume in both states. And we know that in both states, temperature is equal. So we can remove temperature exactly just like last time. And if we were to say this is the pressure in the first state, volume in the first state, pressure in the second state, volume in the second state, single out pressure will give you P1, V1 over P2. And that's 100 kilopascal times V1, 0.4 divided by 0.2. And that gives us pressure of 200 kilopascal. Plug that into the isobaric equation. 200 kilopascal. V3 is 0.6 minus 0.2, so that will give you 0.4 times 200 kilopascal, and that gives you 80 kilojoules. Okay. All right. So now we have work between state 1 and state 2, which was 27.76 kilojoules. Work between state 1, state 2, and state 3, which is equal to 80 kilojoules. And for the net heat transferred, which is actually an equation that I did not give you, it's mCV times delta T. So I didn't give you this equation directly. This will be from state 1 to state 3, but this here should give you a hint that I believe is, if we wait, go back. Yeah, there it is. It's the change. This equation is the change in specific. Well, no, in complete internal energy. So let's assume that this equation is linear. Why is it not? I see a raised hand. I'll answer it right when I'm done with this. So assume this is linear, and this is, and we're taking into account not specific internal energy, but the complete internal energy. You would have mCV times delta T. So it just goes back to this equation. And then this equation, this whole one is just the first law equation. So actually this is a good exercise to practice the first law. So just plus also whenever you see CV, CP, it's a big hint that you might have to use that equation. Okay, so this one will be equal to work that goes from state 1 to state 3, which is just going to be 107.76 kilojoule. CV is given to us right here. The mass is it given to us? The mass is not given to us. Delta T is also not given to us. We don't know temperature in the third state. So we're going to have to find those two values. Okay, so for the mass, we know that we are in an ideal gas. So we can use the ideal gas equation, singling out mass. So mass times gas constant, which in this case is given to us, is equal to pressure times volume. Gas constant is given to us in, gas constant is given to us for all states. Temperature is given to us only in the first state, and pressure and volume as well. But since, well, mass doesn't really change in here, or at least the exercise doesn't tell us that it does, so we can just use it for the first state, and it would be the same for all the other states. So mass is equal to pressure times volume times the gas constant times temperature. And that gives us 100 times 0.4 divided by 0.2081 times temperature, which is 300 Kelvin. That gives you a mass of 0.6407 kilograms. That's your mass. Now to find the temperature, and that's actually just going to be using that same equation we've used for the first state to find, I believe it was, no, for the second state to find the pressure. So P V divided by T is equal to P V T in the next state. So in this case, we're going to use it since we're looking for temperature. Here are delta T. This is the work between state 1 and state 2 and state 3. Sorry, we know the temperature already for state 1, but we don't know the temperature for state 3. So we can either use for the first state. So we can choose P1 times V1 divided by T1 is equal to P3 times V3 divided by T3, or use the second state. In either case, it'll give you the value you'll need. So if we were to take in between state 2 and state 3, we know it's isobaric. So these values cancel out. We're left with V1, T1, V3, T3. And we're only looking for T3, so you can single that out. T3 is equal to V3 times T1 divided by V1, and V3 is 0.6, T1 is 300 Kelvin, and V1 is 0.4. That should give you 900 Kelvin. Or that value doesn't seem correct. Wait, give me a second. Six times 300 divided by 0.4. Yeah, that's not the right value. 450. Okay, so now we have all our values. We can just plug everything in. 0.6407 times CV, which is given to us, 0.3122 times delta T, which is T3, 450 Kelvin minus 300 Kelvin. Or if you want, you can switch back to, actually, no, don't switch back to Kelvin, never mind. We can place the work on the other side. So that'll be plus 107.76 is equal to Q, the net heat transfer, which we were trying to find. And you should find in kilojoule 172.3. There you go. Okay. So I see a raised hand, Yoda. Got a question?
Yeah, I just wanted to find out why the work done from 1 to 2 is a negative. Is it because the system is being compressed?
Yeah. Yes, it is being compressed. You see that from state 1 to state 2, the volume decreases. So we're actually getting work. We're getting work out of this.
Oh, okay, okay.
Yeah.
Sounds good.
Any other questions? Okay. So we'll go over the last exercise for this midterm. Which isn't as long as this one, thankfully. Okay. Ooh. Can we do this one even? I don't think we can do this one. Wait. Sorry, give me a second. Okay, we could go over this one. Although this is some tough shit. Yeah. Okay, all right. I'll see how it goes, and if I see something that wasn't covered from chapter 1 to chapter 4, then I'll stop. But I don't think I see anything. So if we were to, let's say, go back, are we given Q? Okay, no, adiabatic turbine. So that's not only a hint that Q is equal to 0, but you're gonna have to use the first law. So just if we were to go back, first law, Q will be equal to 0. In the exercise, they directly give us work. The mass flow rate is not given to us, but we are given the velocity. And in an adiabatic turbine, most of the time you'll have to assume that the height, well, the height doesn't change because, well, if you were to assume like a, I don't know, a turbine, and the let's say, I don't know, this is the turbine, and the 2 points we're studying is this is state 2, and this is state 1. There's no change in height, so we don't really care. These two cancel out anyway in any case. And then specific enthalpy, which, just like we saw in the previous exercise, can be found using this equation CP instead of CV. Okay, so I'll go over this one. State 1, we are given okay, yeah, sorry. V1 is equal to 50 meters per second. V1 is equal to, let's just say 1.5 megapascal. T1, 450 Celsius. If we were to convert that to Kelvin, would give you 723 Kelvin. At the inlet, we are also given the area of 55 centimeters cubed. And then, well, I'll write that after. State 2, V2, 140 meters per second. V2, much lower pressure, 140 kilopascal. T2 is what we're trying to find, so we don't know it. Area 2, we don't know it. And work from 1 to 2 is equal to 180 kilowatts. And Q from 1 to 2 equal to 0. By the way, kilowatts, or watts in general, is just equal to joule divided by seconds. Oh, actually, wait. I remember having this problem in heat transfer. Is it watts? Just want to check if it's kilojoules. Okay, no. It is joules per second, not kilojoules per second. So watts is equal to joules per second. So just assume it's kind of like mass transfer rate, where you have to divide the mass by the time. You're dividing the joules by time in this case. Okay. So just like we saw before, Q, we don't care. Height, we don't care. Actually, there we go. Okay. So using that equation we studied before, M mass transfer rate initial times specific enthalpy initial plus these velocity squared initial state plus, well, no, we don't care about the height, is equal to the work plus mass transfer rate at the exit, so ME, specific enthalpy at the exit, and then plus velocity squared at the exit divided by 2. So this is how you would transform, well, I guess from your original first law equation. Plus, well, the same thing as here, but for the exit. You cancel out your values because you're told it's adiabatic turbines. Usually you can assume that the altitude doesn't change. Also the exercise, nowhere does it give you the height. So yeah, okay, so what are the values we don't know? We don't know specific enthalpy, we don't know the mass transfer rate, and yeah, those are the two values we don't know. So how do we get those? Once again, argon and ideal gas. So for the mass transfer rate, we're going to assume in this case that the mass transfer rate is going to be the same going in and going out. This is usually the case for turbines, and I think this is where the exercise starts to be not part of chapter 4. You're going to go later on, I believe in chapter 5, in later chapters, you're going to study a little bit about turbines, and these assumptions will be made clearer in the theory. But so, this is still like a pretty good exercise just to review for other stuff, especially the first law equation. So in both states, the mass transfer rate is the same. So how do we get it? Using the ideal gas equation, we can find the specific volume. So in the first state, it will be equal to R times the temperature times P1. So in this case, 0.2081 times 723 Kelvin divided by the pressure, which is 1.5 times 10 to the power 3. And that gives you 0.1003 meters cubed divided by kilogram. Now with that, with the specific volume, you could find directly the mass. So in this case, mass is equal to, sorry, without the dot, my bad, will be equal to V1 or VI by a specific volume. So, but in this case, we're not given the volume, so we can't use this equation. We have to find another equation, which again, you'll be studying once. Oh, my bad. Once you go further in other chapters, there'll be this equation. The mass transfer rate will be equal to the area at the inlet times the velocity at the inlet divided by the specific volume. So now if you were to study this by units, meters cubed for the area, velocity is meters time per second, and specific volume is meters cubed divided by kilogram. And that gives us kilograms per second, which is the unit for mass transfer rate. So if we were to plug in all the values, which we know, 55 centimeters cubed, we want in meters. So normally from centimeters to meters, you would do 10 to the power of -2, but since it's centimeters cubed, you cube that as well. So it would be 10 to the power of -4, and times the velocity, which is 50 meters per second, and the specific volume, which we just found, 0.1003. And that gives us 2.742 kilograms per second. Again, I didn't see this in any of your notes for chapter 4, so don't worry about this. Just forget about it for now. I just want to cover this because the first law equation is used here, and it's pretty useful to study that. We didn't cover any of the first law equations exercises last week. Okay. All right, so now we have mass transfer rate. The other unknown that we don't have, in this case, just like I said before, specific enthalpy, H. And just as we said before, and actually what we use for the specific internal energy, but this time just do the exact same thing for specific enthalpy. Assume that it is linear. So you can derive this equation. CP, I guess this is going to be between state 1 and state 2, so T2 minus T1. And we know CP, we don't know T2, but that's what we're trying to find, and T1 we don't know as well. So if we were to plug everything back into the first equation, but reforming it, knowing that the mass transfer rate is equal for both states, we can write it as this is equal to delta H plus delta V squared over 2. That will be equal to CP T2 minus T1, with T2 being the one that we're trying to find, plus V squared V2 minus V1 V squared divided by 2. Okay. And then you plug in all the values, 2.742, CP 0.5203, T2 is the one we're trying to find, minus T1, which was 723 Kelvin, plus So 140 squared minus, what was it, 50 squared. Okay, that's fairly long. Oh yeah, and well, that's equal to 180 kilowatts. If you were to single everything out, you would just get T2 is equal to 580.4 Kelvin. So ideally, the way the teacher would reformat this question is that mass transfer rate would be given to you, and they would give you the hint that mass transfer rate is equal in between the two states. So those are the two parts that I didn't see are actually going to be part of upcoming chapters. Any questions regarding this one? Okay, well, if you guys don't have any questions, I did not prepare anything else. That was the maximum. If you still have any questions, I'm going to stick around